So in the last video, we saw the relationship between x hat of t, right, our updated version of x of t, with respect to our predicted version of x of t, which is x bar of t, and all we said was that x hat of t was equal to x bar of t plus the Kalman gain times our observed measurement, or our observed measurement minus our predicted measurement. And again, I covered this in the last video. I just want to recap that this is what we covered. And in this video, I want to cover the covariance matrix that I started talking about in the last video, which was P equals the covariance between our actual state, which we don't know, minus our updated time step at t, our updated state at time t, which is denoted by x hat of t. So I wanted to explain a little bit more about this covariance matrix. If we wanted to get a visual of this covariance matrix, we can see that we can draw a little picture. And on the on-diagonal elements, we'll get the variance, which is sigma squared, of each of the things that we're measuring in our vector for the state. So we're measuring position in the state, and we're also measuring velocity in the state. So we'll get the variance, which is sigma squared p, and the variance for velocity, which is sigma squared v. These are on the main diagonal elements, and on the off-diagonal elements, we'll get the covariances between these two. So I'll just label this as covariance of v with respect to p, and the covariance of p to v. Right, so this is how we can picture the covariance matrix. And the items of importance are these on diagonal elements, the main diagonal elements right over here. So why is the case? Why is this the case? Well, if we think about the goal of the Kalman filter, right, this measurement right here, which is the variance, is going to tell us how uncertain we are about our state, right? How uncertain and how far apart these things are, how far apart our actual state versus our updated state is. So if these things are large, we're not very certain about our estimates, and we're not very sure about where we are. However, if we can minimize these things, then that means that we have a pretty good estimate, and we're pretty sure as to where we are, and that we can make good predictions in the future, which is the whole goal of the Kalman filter to begin with. So the main goal of the Kalman filter, if you want to think of this as an objective, is to minimize the sum of these variances. So minimize basically the sum, I'll write in summation term, of the variances. I'll just do variances in the covariance matrix P. Right now, if we want to be a little bit more mathematical, we can say that this is the same as minimizing, right? This is equivalent from going from I equals 1 to n, assuming that, I guess, the covariance matrix is an n by n matrix of Pii, right? This is just going to insert Pii is going to be the next on diagonal element. So the sum of the on diagonal elements actually has a nice name in linear algebra, which is known as the trace of a matrix. So this is equal to the trace of P, which is oftentimes just referred to as TR of P, which stands for trace of P. So now we found a nice mathematical optimization objective of this Kalman filter, which is really to minimize the trace of this covariance matrix P. And we can see why, right? If we can minimize the sum of these things, then that means that we're minimizing our inaccuracy, our uncertainty. We're pretty much saying that we're very certain as to where we are, and we can make accurate predictions. So this throws in a nice new level of mathematical certainty, right? This is what we're trying to do. Minimize the trace of this covariance matrix P. And we're also going to have to do this by figuring out this Kalman gain K, right? Which I mentioned in the last video. It's going to help us towards nudging this X, right? This updated state X. So we actually have to solve things in terms of K first, in order to get good estimates for our updated, in which case it will help us update our covariance matrix P. So everything kind of relies on this Kalman gain matrix K. So let's begin. All right, this is a very involved proof, I understand this. So if at any time you have a little bit of trouble or you want to go back, please do. But I think that if you watch this video closely, it should be no problem. So let's start by rewriting the definition of the covariance matrix P. I think this is a covariance of xt, right? Xt minus x hat of t. But what is x hat of t really? X hat of t is this equation right over here, which we just saw, right? And we explained it in the last video. So I'm actually just going to copy this definition for x hat of t in here. So we get minus x bar of t plus k times zt minus z bar t, right? So we're just literally plugging in the definition for x hat of t. Now, we could also expand these two things right here, z of t and z bar of t, because we explained what z bar of t was, right? We also gave the equation for z bar of t. Z bar of t was just c times x bar of t. And we covered this however many videos ago, but we covered this, right? However, what we didn't cover was how we can also get a formula for zt, right? Because really what we said was we're just going to pick this up from the sensor. But in the similar way that we estimated what our sensor was, right? We plucked off the position with this matrix C of our estimated state x bar of t. Similarly, if we somehow knew xt, right? If we somehow knew our actual state, we can say this is the exact same thing, right? We can say that our actual sensor reading will be just plucking off the position from our actual state. But since our sensors are noisy and we always have to measure noise, we'll also add in a noise factor Vt. And this is just the noise from the sensor. So we're plucking off the position, but we're adding some noise. So we can actually model Zt with this equation right over here. Right? Even though it may not look like it originally, and even though this is not exactly how we get Zt, we actually pick up Zt from the sensor, we can model Zt in this way. So now if we want to plug in the definitions of Zt and Z bar of t into this new covariance matrix definition, what we'll get, actually I have to write this kind of small because this is a pretty big equation. We get that P is the covariance of xt minus x bar of t plus the Kalman gain k times, well, what is Zt? We said it was equal to x, or cxt plus Vt minus cx bar t. And this is what we said. We said that this is P is equal to the covariance of this thing. And now if we were to expand this, right, which I'll attempt writing on this space, the next thing we want to do is actually expand this. So if we expand this, what we get is that this is equal to covariance of xt minus, and I'm actually going to distribute this negative, so minus x bar t minus k times cxt, so minus k cxt minus k vt, and then really what we get here is negative k cx bar t, but we're multiplying it by negative, so here we get plus k c x bar of t. Okay, so I just multiplied things together, and similar to how in an algebraic equation we can group together like terms and start taking out certain things, certain common expressions, here we can do the same thing, except we're dealing with matrices. We're not exactly dealing with expressions and things in terms of x or y or anything. So we actually have to do this in a slightly different way, so I'll do it in a different color. We see that this is exactly equal to the covariance between the identity matrix I, and I hope you know the identity matrix, minus this Kalman gain k, which we saw over here, times c times x of t minus x bar of t, minus x bar of t. And to this, we're actually going to subtract k v t. All right? So let's take a minute to process this. This is exactly how you would, we're putting together like terms. And why is this? Because we see an xt here, we see an x bar t here, we see another xt here, and an x bar t here. And we see common terms, right? We see that on the xt we have a kc, and on the x bar of t we also have a kc, and we also have a normal xt and a normal x bar t. So we can actually just group together these terms, and the identity matrix in linear algebra is the same. You can think of it conceptually as like a 1 in an algebraic expression. So the identity matrix times this matrix will actually just give you back this matrix, and this is just standard linear algebra review. So if you expand this, what you'll get is xt minus x bar t minus kcxt plus kc x bar t, which is exactly this. And then what we left out was this minus kvt, which we've compensated for over here. So far, so good. Now, similar to how in calculus, when we're doing with integrals, if you have, for example, the integral of 5x plus 2, you can actually split up this integral, right? Because this 2 really has no bearing on the 5x. This is the same thing with covariance matrices. We can say this is exactly equal to the covariance between, well, what? We see that this kvt is really just constant, right? Because we're never changing the Kalman gain k. We're trying to solve for it, and this noise is probably never going to change. So this expression here really has no bearing on the rest of this. So we can actually just change this to the covariance between I minus kc times xt minus x bar t, right? Plus the covariance of k times vt. All right, and I'm out of time in this video, but in the next video we'll continue this derivation.